So one of the things we noticed about finding our derivative at a point in the previous video was that we didn't have to specify the point ahead of time. We could go ahead and kind of put it in a general sense, and then we would have some way of figuring out what the derivative was for whatever x value we wanted to know about it at. So what we're going to do is we're actually going to consider the derivative itself a function. So recall that our definition for derivative at an individual point was f prime of a, which could either be the limit as h approached 0 of f of a plus h minus f of a over h, or it could be f prime of a equals the limit as x approaches a of f of x minus f of a all over x minus a. And you might have noticed in the last video I was kind of leaning on this definition a little bit more. I did that for two reasons. The first reason is that it's a little easier to go ahead and just find a common factor of h at the end of the day and cancel it out. That's a lot easier than trying to find this x minus a over here to have to worry about. However, the other reason is that this is the definition that more extends naturally into our limit definition of the derivative becoming a function. So if we want to go ahead and find a derivative for a function to make the derivative itself a function, what we're going to do is we're going to call it f prime of x. So at that point you can specify whatever x value you want. And this is the limit as h approaches 0 of f of x plus h minus f of x all over h. So if it's a function, it's going to have its own domain, its problem points. We have to figure out whether or not the domain will work. So let's say we wanted to find the derivative of the function f of x equals the square root of x, and then find the domain of that derivative. So then f prime of x will be the limit as h approaches 0 of f of x plus h minus f of x all over h. And so remember, when we're taking the function and we're plugging in something like x plus h, that means that anywhere there's an x, we replace it with x plus h. So this becomes the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. Now remember that when we have these kind of awful square roots like this and we're trying to take a limit where we can't go ahead and plug in immediately, our typical response is going to be to try to find the conjugate. And so what we want to do is we want to find the conjugate of this and multiply the numerator and denominator by that conjugate. So this will be square root of x plus h, and then since it's a minus square root of x, it'll be plus square root of x over square root of x plus h plus the square root of x. And so in doing this, we'll go ahead and FOIL the numerator out. So bringing this over here, we get the limit as h approaches 0 of square root of x plus h times the square root of x plus h will just be x plus h. Then multiplying by this will be plus square root of x times the square root of x plus h, and this will be minus square root of x times the square root of x plus h. So the outer terms and the inner terms, as always when we do this, will cancel. And then multiplying the last two together will be negative square root of x times the square root of x, which will be minus x. And this will be all over h times square root of x plus h plus the square root of x. And so in the numerator, the x and the negative x will cancel. And then that'll just leave h over this mess, and the h's will cancel. And so we'll just be left with limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. And now when we plug in this limit and let h be 0, we'll get 1 over the square root of x plus the square root of x, or just 1 over 2 square root of x. So this is going to be the f prime of x. Let me maybe write that a little bit clearer. So that means f prime of x equals 1 over 2 square root of x. And so now, if you want to find the domain for f prime of x, you're going to find the domain the same way you would for any function. So you'll ask the two questions that you ask for domain. Question 1, is there a 0 in the denominator? If so, we cannot have that. And 2, is there a negative under a square root? And so with that, the domain hopefully will be something that we're pretty comfortable with because this is just a function. If you have questions about it, I definitely recommend asking about them on the discussion board and I can explain it a little further. But the derivative has a domain in this case of 0 to infinity. And we won't include the 0 because that would mean that we would divide by 0. So it only can be the positive numbers, or really the non-negative numbers because of the square root, but then it can't be 0 because then we'd divide by 0. So that would be a problem. And part of the reason we call this a derivative of a function f is because it has been derived from that function. It's just a little bit of a sense of why we choose our definitions the way we do. Okay, some other things about the derivative then. So let's say we wanted to look at the function, this function here, and we wanted to use its graph to sketch what the derivative is going to look like. So when we're trying to sketch the derivative, this red line that I'm about to draw is going to be what the derivative looks like. So, or actually, I'll just go ahead and draw another one below. That would maybe make more sense. So our derivative is going to be basically what the slope of the line is. So when we are going from just below 0 up until whatever this point is, we're going to call it a for now, our slope is actually negative, right? So our values are going down, and so until we get to whatever this point a is, we should have a negative slope. And though it looks like it's a bit of a larger one, and then it looks as though it tapers off until it gets to 0. So we'll have something that looks like this. So it'll be below. So this is going to be for our y equals f prime of x graph. And then from there, between this a and whatever this next point is, we're going to call it b, it looks to be increasing. Now, somewhere in the middle, between a and b, it looks as though it goes from going up to going down. So for now, we're just going to go ahead and say that it kind of goes up, and then it goes down. And then it goes back to being negative again until we get to whatever this point C is. And so again, we're going to go back to being negative, 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 and then after a while, we'll get back, and we'll get to wherever this point C is, and we'll be going back to having zeros again. So every time we have these horizontal tangent lines, we're going to go ahead and have our slope be 0. So horizontal tangent lines have a slope of 0. And so our negative slopes are going below the x-axis, and our positive slopes are going above the x-axis. And then from here, the rest of the way, we are positive. So we can just kind of keep increasing for however long we keep increasing. So just make sure we say that. Negative slope for f of x leads to a f prime that is negative, and a positive slope for f of x leads to an f prime that is positive. Now there's more than one way of writing the derivative. So here we have presented 4 different ways. The first 2 are referred to as prime notation. And the reason for that is this little dash here. We call that the prime. So we say f prime of x or y prime. Either way, this is saying the derivative of whatever f of x or y is. These second types we call differentials. And in the differential, what we're saying is we're taking the derivative of some function with respect to some variable. So what we're saying with this first one is the derivative of f with respect to x, and the second one is saying the derivative of y with respect to x. So either way will get used, either the prime notation or the differentials. Now you might be thinking to yourself, oh, okay, why are there so many different ways to do this? Well, this is a lot cleaner to write. This is a lot less work. This gets a lot more useful if you ever take a higher level of calculus where you start dealing with functions with more than one variable. Wait a minute, we can have functions where there's more than one variable? Yeah, turns out we can totally have functions where there are multiple different types of inputs to get a single output. Well, that sounds terrifying. Yeah, it is. We'll probably see some of those next week. Don't worry, you'll be fine. Nothing will be scary. Alright, so definition time. When the limit is used in the limit definition of the derivative, when this limit exists for a function, we say that the function is differentiable. At x equals a. So, in other words, what we're saying is, if we try to take the limit and it exists at some value x equals a, it's differentiable. If that limit doesn't exist, we say it is not differentiable or non-differentiable. At that value. So there are a few different reasons why a function might not be differentiable at some a value or some x value. So one reason could be f is not continuous at x equals a. Another might be if the function f has a sharp point at x equals a, and one more reason might be that f has a vertical tangent line at x equals a. All right, so recognize that when we're trying to go ahead and come up with our limit definition, we need f of a to exist in order for us to be able to find the derivative. So if it doesn't exist where we think it's supposed to, that breaks up the continuity and that causes problems with trying to find our derivative. Again, we also have derivative or issues with the derivative if we ever have some sort of thing like this, where we have a sharp turn. Because what that means for us is that our limit of our slopes going this way and our limit of our slopes going this way are going to be very different, and so it won't be possible for us to get that tangent line. And again, if we have a vertical tangent line, that's also going to be an issue for us when trying to go ahead and find our limits. So notice that you can't have something that's differentiable if you're not continuous. What that means is that the contrapositive or the opposite of that statement is true. So a nice little theorem we get is that if a function f is differentiable at x equals a, then f is continuous at x equals a. Alright, so then let's go ahead and figure out, based on the graph of this function, where we're going to have issues with the continuity. So we want to know where this function is differentiable. So really, what we're asking, instead of asking where it's differentiable, is where does it have problems? So another way to think about it is, where are the problems? If you can answer where the problems are with the differentiability, then you've answered the question of, or you can answer the question of where it's differentiable. So if we take a look here, we're looking out for sharp corners and any sort of places where we don't have continuity and where we have vertical tangent lines. So it doesn't look like there's any vertical tangent lines here, but if we look here and here, we have two sharp corners. So we've got sharp corners at x equals 2 and x equals 4. And when we look at x equals 6, the function is not continuous at x equals 6. So these three places are where the problems are. So that means we're differentiable everywhere else the function exists. So that means it is differentiable on negative infinity to 2, 2 to 4, 4 to 6, and 6 to infinity. So again, anywhere where those problem points aren't, we can go ahead and find the derivative. Now notice that we've now started calling the derivative of a function itself a function. But since the derivative is a function, it also has a derivative. So the derivative of our derivative is going to be denoted as f double prime, which is the derivative of f prime, sometimes called the second derivative of f. Now note, instead of doing f double prime, you could also do the second derivative of the function with respect to x. The differential notation is a little bit clunkier, but we don't have to stop at the second derivative. We can even go to our third derivative. So this is the derivative of f double prime, or the third derivative of f. And so here, using the differential notation, this would be d3f over dx cubed and we also could have the fourth derivative. Now once you start getting to the fourth derivative and higher, instead of using these prime marks, you might see an in parentheses number here. Now notice that when the number is in parentheses, this means we're talking about a derivative, not an exponent. So this is the derivative of f triple prime, or the fourth derivative of f. And again, the differential notation here would be d4f over dx4. So in general, as a definition, let n be an integer, some sort of whole number. The nth derivative of the function y equals f of x will be f in parentheses n of x, or dnf over dx to the n, if you want the differential notation. So this is the prime notation, this is the differential notation. You'll most likely see this more often, but this will show up more in multivariate examples. Now when we're talking about the derivative from a standpoint of distance and height, so if it's representing some sort of position, which will typically happen more in physics problems, then the first derivative will be called v of x, and this is the velocity. So that's the rate of change of the position. The second derivative is a of x, which is the acceleration. And the acceleration measures how quickly the velocity is changing. The third derivative, which is less well known, and of course this is v prime of x as well. The third derivative of the position function, which is less well known, is the second derivative of the velocity, the first derivative of acceleration, and it's actually called j of x, also known as the jerk of the function. So this is the rate of change of the acceleration. Now, of course, because physicists like to come up with fun names, after jerk, I believe, is snap, and after snap is crackle and pop. So if you wanted to keep taking derivatives and you like Rice Krispies, those are those even further derivatives, 4th, 5th, and 6th, I believe. You can look that up to verify it. I'm sure it's totally true. All right, so one last example then, before we close out for this section of notes. We have the graph of three functions. One of them is the position, one's the velocity, and one's the acceleration. And we want to know which is which. So we've got f, g, and h. So what we're going to do is we're going to actually lean on the horizontal tangent lines, which I'm just going to denote as HTL, to find the zeros for derivatives. Alright, so let's look at each of these and try to find their horizontal tangent lines. So if we look here at H has a horizontal tangent line here, And what that means is that we would expect this function g to be its derivative. So it looks like h prime is going to equal g. And if we look at g, it looks like it has a horizontal tangent line here and here. So if we look, in both of those x values, f is going to be 0. So it appears that g prime is f. So that means then that we would expect our position to be h, our velocity to be its derivative g, and the acceleration to be f. And so as we're looking at this, recall that the derivative is going to be your slope of the tangent line. So as we look at h goes up and then it does nothing but go down. So then for g, we expect g to be positive, and then when it starts to go down, when h starts to go down, g should only be negative. Now again, we're looking at f. F should go ahead and have its positive and negative parts where g begins to rise and fall. So g starts off positive, so should f. And then when g tapers off and starts to decrease, f becomes negative, and g continues to decrease all the way until we get to here. Once we get to here, f becomes 0, and g starts to go up at the end, and so does f. So just some things we can kind of keep in mind as we're trying to match which of these functions it is with its respective graph.